Hello everyone, this is our walkthrough for week 12's discussion board, the competing population crisis. For question number 1, we were asked to show where the equations that were given to us, where they came from. We're given dx dt is equal to negative 0.25x minus 0.3y plus 2. And we were also given dy dt is equal to negative 0.2x minus 0.36y plus 1.7. So what I did was just pulled up the information that was given to us and went through and highlighted each part of the equation to just show where it came from. So the first part I highlighted was that each beta is capable of eating on average 0.2 tetras per unit time. So we have that here in the tetra equation, negative 0.2x. The x would be the betas. Since the betas are eating the tetras, that's why that term is there. Then we have each tetra is capable of eating on average 0.3 betas per unit time. So that's why we have the 0.3y, the negative 0.3y in the beta equation. The y would be the tetras, and since they are taking out the betas, it's negative. The next thing I highlighted was that betas are dying off at a rate of 25% per unit time. So you have the negative 0.25x in the beta equation. It's negative because they're dying off. The next thing I highlighted was that tetras are dying off at a rate of 36% per unit time. And that's where we get the negative 0.36y in the tetra equation. Then I highlighted that the betas are being restocked at a rate of 2 betas per unit time. So that's where that 2 comes from in the beta equation. And then I highlighted that the tetras are restocked at a rate of 1.7 tetras. 7 tetras per unit of time, and that's where we get the 1.7 in the tetra equation. For question 2, we were asked to find the equilibrium point of the system and then explain what it means in this context. So we have dx dt is equal to 0.25x minus 0.3y plus 2, and dy dt is equal to negative 0.2x minus 0.36y plus 1.7. To find the equilibrium points, we want to set both of these equal to 0 and then find an x and a y value that makes them equal 0 simultaneously. Find the easiest way to do this is just plug it into Wolfram Alpha. And we get 7, and then for our x value, and then the y value we get 0.833. In this case, that is when the populations will essentially level out. They'll be dying and coming in at the same rate. The rate of change will essentially be 0. And then for number 3, we're asked to find the homogeneous solution of the system. So we'll start off with the equations that were given to us. And to find the homogeneous solution to the system, we have to take out the non-homogeneous part. In our case, that is the 2 in the dx dt and then the 1.7 in the dy dt. So our new equations will be negative 0.25x minus 0.3y is equal to 0, and negative 0.2x minus 0.36y is equal to 0. Then from there, we want to use those terms to create a vector to plug into Wolfram Alpha to get our eigenvalues and our eigenvectors. After doing that, we get that lambda 1 is equal to negative 0.556, lambda 2 is equal to negative 0.0539, and then we have both of our eigenvectors there. Then to write our solution now after we get our results, we write out y of t is equal to k1 times e raised to lambda 1 times eigenvector 1 plus k2 times e raised to lambda 2 times eigenvector number 2. And then from there we'll use these values to distribute, we'll get x of t is equal to 0.98 times constant 1 e raised to the negative 0.56t minus 1.53 times constant 2 times e raised to the negative 0.054t. And then we get y of t is equal to constant 1 times e raised to the negative 0.56t plus constant 2 times e raised to the negative 0.054t.
Okay, so this is question 4. Find the non-homogeneous particular solution to the system. So basically, all we really have to do here is take the original equations and set them to 0 and solve the system, which I did using Wolfram Alpha. And then you get the following, which is the equilibrium point. And for question 5, we have to write the general solution to the system of ODEs and then also solve them for their initial conditions and solve for the constants. So I started with the results that we got from question 3, and then I solved those. I evaluated them. At the initial conditions right here, and that led me to this result here. 10 equals 0.98 k1 minus 1.53 k2 plus 7, and then for the y equation, 5 equals k1 plus k2 equals 0.833. And then we plug that also into Wolfram Alpha to solve the system, and then we get the value of k1 and k2, and then we plug those values into those equations up here, and we get our general solution. And for question 6, based on the solution, what happens to the populations over a long run? This is the Desmos graph. Ignore that x equals 80. I just did that to kind of show, as time progressed, we're approaching a value of 7 for the x equation and a value of 0.833 for the y equation. The right equation is actually, the x is actually increasing to that value, and then the y equation is actually decreasing to that. Yeah, I hope that all made sense. I'm going to pass it off now to my other member from our group, and he'll finish up.
For question 7, the question asks, suppose we had a greater number of betas and tetras than in question 5. Let x of 0 equal 300 and y of 0 equal 600, meaning that we're starting with 300 beta and 600 tetras, and find the values of the arbitrary constants once again. So how you would solve this is you would substitute 300 for x of t and 600 for y of t, and you would solve for the constants at that point. You can either solve those for them algebraically, or can you solve them using Wolfram Alpha. We ended up solving it using Wolfram Alpha, and we got that K1 is equal to 117.205 and K2 is equal to 481.962, resulting in the equations for x of t and y of t as shown here. For question 8, the question is, does the long-run behavior of the two populations change relative to what you concluded in 6? We plotted the solutions here, as you can see in our graph below. And as expected, the solutions did end up, in the long run, end up being the same. For the betas, as x, or in the equation, t got very large, the equation approaches the value of 7. And for the tetras, as t got very large, the tetras reached the value of 0.83. And for the final question, the question asks, we're noticing that the initial conditions do not seem to influence the long-run behavior of the two populations. Why does this make sense? And is there a connection to question 2? And yes, there is a connection. That is the equilibrium points. The equilibrium point, as we remember in question 2, was 7 for the x value and 0.833 for the y value. This is when the betas and tetras are no longer being added, eaten, or dying, and the change will be 0.